Yield predictor can inflate, manufacturing yield forecasting model with economic and inflation factors. The implemented AI/ML model provides a valuable tool for decision support systems, DSS, in management by forecasting manufacturing yields and visualizing their relationship with external factors like inflation and economic growth. Here's how the program can aid management in a DSS. Pradeep K. Suri. Model Architect. Author, Researcher, and AI DNN Architect. 1. Forecasting and Planning. Yield forecasting. The random forest model predicts future manufacturing yields based on historical data and external factors. This helps management anticipate future production outcomes and make informed decisions about capacity planning, resource allocation, and budgeting. Scenario analysis. By adjusting external factors like inflation and economic growth, management can explore different scenarios and their impact on manufacturing yield. This enables them to prepare for various economic conditions and make strategic adjustments. 2. Understanding external impacts. Inflation and economic growth analysis. The program includes external factors in the forecast model, allowing management to see how changes in inflation rates and economic growth affect manufacturing yields. This insight helps in understanding the broader economic environment and its impact on production efficiency. Dual-axis visualization. The use of Plotly's dual-axis chart allows management to visualize the manufacturing yield alongside external factors. This visual representation makes it easier to correlate changes in yield with fluctuations in inflation and economic growth, providing a clearer picture of external influences. 3. Improving decision-making. Data-driven decisions. The program leverages machine learning to provide data-driven forecasts. This reduces reliance on intuition and anecdotal evidence, leading to more accurate and reliable decision-making. Risk management. By forecasting potential yield outcomes and understanding the impact of external factors, management can identify risks and opportunities. This allows for proactive measures to mitigate risks or capitalize on favorable conditions. 4. Strategic planning. Budgeting and financial planning. Accurate yield forecasts help in setting realistic financial goals and budgets. Management can plan for changes in production costs and revenues based on predicted yields and external economic conditions. Resource optimization. Understanding future yield trends helps in optimizing resource allocation, such as adjusting inventory levels or workforce planning to match anticipated production needs. 5. Communication and reporting. Interactive visualizations. Plotly's interactive charts make it easier to present complex data in a clear and engaging manner. Management can use these visualizations in reports and presentations to communicate forecasts and analysis to stakeholders effectively. Scenario comparison. The ability to visualize different scenarios with external factors enables management to compare potential outcomes and make informed choices about strategic directions. Summary. The program enhances the decision support process by providing predictive insights, forecasting future manufacturing yields based on historical data and external factors. Visual analysis, clear visual representation of how external factors impact manufacturing yields. Data-driven planning, informing strategic decisions and planning with accurate, data-driven insights. Risk management, identifying and managing risks associated with changes in external economic conditions. Overall, this approach helps management to make well-informed, data-backed decisions that align with their strategic goals and adapt to changing economic conditions. From a management perspective, understanding the use of four-fold cross-validation in the random forest model can offer several insights into how the model's performance is evaluated and how this information can be utilized for decision-making. Here's a breakdown. 1. Model evaluation and reliability. Cross-validation purpose. The four-fold cross-validation process helps in assessing the model's performance more robustly than a simple train-test split. It provides a better estimate of how well the model will perform on unseen data by using multiple train-test splits. Reliability of results. By dividing the data into 4 parts and rotating the test set, you ensure that every data point is used for both training and testing. This reduces the risk of overfitting, where the model performs well on the training data but poorly on new data, and provides a more reliable measure of the model's accuracy and robustness. 2. Decision-making and risk management. Informed decisions. the performance metrics obtained from cross-validation, example negative mean squared error, help management understand how well the model predicts future manufacturing yields. Reliable predictions support informed decision-making in areas such as budgeting, resource allocation, and strategic planning. Mitigating risks. By evaluating the model's performance with cross-validation, management can better gauge the risks associated with relying on the model's forecasts. A well-validated model is less likely to provide misleading predictions, which reduces the risk of making decisions based on inaccurate forecasts. 3. Resource allocation and efficiency. Optimal use of data. Cross-validation makes efficient use of available data by ensuring that each data point is used for both training and testing. This is particularly important for small data sets, where maximizing the use of data is crucial for building a robust model. Computational efficiency. Using fourfold strikes a balance between computational efficiency and model evaluation. While it may require more computational resources than a simple train-test split, it is less intensive than higher fold numbers, example tenfold, and provides a good compromise between accuracy and resource use. 4. Communication and reporting. Clear metrics for stakeholders. The results from cross-validation, such as the mean squared error, can be used to communicate the model's performance to stakeholders. This helps in explaining the reliability of the forecasts and the expected accuracy of the predictions. Transparency. Cross-validation provides a transparent method of evaluating the model. By showing that the model's performance has been tested through multiple folds, management can be confident in the validity of the results and the model's ability to generalize to new data. Summary. In summary, from a management point of view, fourfold cross-validation in the random forest model provides a more reliable estimate of model performance, ensures that predictions are based on a robust evaluation method, leading to more trustworthy forecasts. Informed decision-making, offers valuable insights into future manufacturing yields, helping in strategic planning and resource allocation. Efficient data use, maximizes the use of available data, especially important for small data sets. Enhanced communication, facilitates clear communication of model performance to stakeholders, supporting transparency and trust in the forecasting process. By understanding and utilizing the results of cross-validation, management can make more informed, data-driven decisions and effectively manage risks associated with manufacturing forecasts. To compare the results of fourfold and fivefold cross-validation, you need to run the model with both configurations and analyze the performance metrics obtained. Here's a step-by-step comparison approach. 1. Implementing fourfold and fivefold cross-validation. Below are the two programs, one with fourfold cross-validation and the other with fivefold cross-validation. It looks like the results from the fourfold cross-validation program are as follows. Fourfold cross-validation results. Cross-validation scores, negative MSE -7.7284, -0.0676, -7.6176, -0.04. Interpretation, these scores indicate the negative mean squared error, MSE, for each fold. Since MSE is always positive, the negative values show how much error the model had on average across each fold. Larger negative values indicate poorer performance. Forecasted manufacturing yield for test set, 24.88, 25.44. Interpretation, these are the predicted manufacturing yields for the test data. Mean squared error for test set, fourfold 17.824. Interpretation, this is the average squared difference between the actual and predicted values for the test set. Higher values indicate worse performance. Future forecasted manufacturing yield for 2027 to 2030, 29.24, 29.24, 29.24, 29.24. Interpretation, these are the predicted yields for the future years based on the model. Fivefold cross-validation results. If you have the results from the fivefold cross-validation as well, you can compare them similarly. Typically, you will see cross-validation scores, compare these to see if the fivefold results are more consistent or if they have a lower mean negative MSE, indicating better model performance. Mean squared error, Check if the MSE for the test set is lower with 5-fold cross-validation compared to 4-fold. A lower MSE indicates a better model fit. Future forecast: compare these forecasts to see if there are significant differences between the two approaches. Comparison analysis. 1. Model performance. 4-fold, the MSE is quite high at 17.824, indicating that the model may have high errors on the test set. 5-fold, if the MSE is lower in the 5-fold cross-validation, it would indicate that the model performs better with more folds. 2. Consistency and stability. 4-fold, the large negative MSE values indicate significant variation in model performance across folds. 5-fold, more folds usually provide a better estimate of the model's performance by averaging over more subsets of the data. 3. Forecast accuracy. Future forecast: if the forecasts differ significantly between 4-fold and 5-fold, it could suggest that the number of folds affects how well the model generalizes to new data. 4. Computational cost. 4-fold vs 5-fold, while 5-fold provides potentially more reliable results, it is more computationally expensive. If the improvement in performance is minimal, 4-fold may be sufficient. Summary. In summary, comparing 4-fold and 5-fold cross-validation results helps assess the trade-off between computational efficiency and model evaluation accuracy. If 5-fold cross-validation shows better or more consistent results, it might be worth using despite the additional computational cost. If there's no significant improvement, 4-fold cross-validation could be a more practical choice. 3-fold result. 3-fold cross-validation scores: negative MSE-13.3904-7.6176-0.04. Forecasted manufacturing yield for test set: 24.88 25.44. Mean squared error for test set: 3-fold 17.824. Future forecasted manufacturing yield for 2027 to 2030: 29.24 29.24 29.24 29.24. 4-fold result. 4-fold cross-validation scores: negative MSE-7.7284-0.0676-7.6176-0.04. Forecasted manufacturing yield for test set: 24.88 25.44. Mean squared error for test set: 4-fold 17.824. Future forecasted manufacturing yield for 2027 to 2030: 29.24 29.24 29.24 29.24. Comparison of the results between the 3-fold and 4-fold cross-validation scenarios. 3-fold cross-validation results. 3-fold cross-validation scores: negative MSE-13.3904, -7.6176, -0.04. These scores indicate the mean squared error of the model in each of the 3 folds. Lower absolute values of negative MSE are better. Forecasted manufacturing yield for test set: 24.88, 25.44. Predictions made by the model for the test set. Mean squared error for test set: 3-fold 17.824. This is the average squared difference between the observed actual outcomes and those predicted by the model on the test set. Future forecasted manufacturing yield for 2027 to 2030: 29.24, 29.24, 29.24, 29.24. Predictions made by the model for future years with given external factors. 4-fold cross-validation results. 4-fold cross-validation scores: negative MSE-7.7284, -0.0676, -7.6176, -0.04. These scores indicate the mean squared error of the model in each of the 4 folds. As with 3-fold, lower absolute values of negative MSE are better. Forecasted manufacturing yield for test set: 24.88, 25.44. Predictions made by the model for the test set. Mean squared error for test set: 4-fold 17.824. This is the average squared difference between the observed actual outcomes and those predicted by the model on the test set. Future forecasted manufacturing yield for 2027 to 2030, 29.24, 29.24, 29.24, 29.24. Predictions made by the model for future years with given external factors. Comparison. 1. Cross-validation scores. Threefold cross-validation scores, the MSE values are more varied with one significantly larger negative score. This could indicate more variance in model performance across the folds. Fourfold cross-validation scores, the MSE values are closer to each other, suggesting more consistent performance across the folds. The scores are more balanced compared to the threefold results. 2. Mean squared error for test set. Both threefold and fourfold cross-validation scenarios have the same MSE for the test set, 17.824. This indicates that, despite the different cross-validation approaches, the model's performance on the test set remains consistent. 3. Forecasted manufacturing yield. Both threefold and fourfold scenarios provide identical future forecasted values for 2027 to 2030, 29.24, 29.24, 29.24, 29.24. The forecasts are the same because the future data predictions are based on the same model, which does not change between the cross-validation setups. Conclusion. The choice between threefold and fourfold cross-validation may affect the variance in model evaluation metrics, but it does not change the predictions for the future or the test set MSE in this case. In general, increasing the number of folds, to a reasonable extent, can provide a more reliable estimate of the model's performance by using more of the data for training and testing. However, for very small data sets, increasing the number of folds beyond a certain point can lead to issues such as having too few samples in each fold. In your case, fourfold cross-validation provides slightly more balanced cross-validation scores compared to threefold, but both methods lead to the same future forecasts and test set performance. Fourfold cross-validation scores, negative MSE-7.7284 minus 0.0676 minus 7.6176 minus 0.04. Forecasted manufacturing yield for test set, 24.88 25.44. Mean squared error for test set, fourfold 17.824. Future forecasted manufacturing yield for 2027 to 2030, 29.24 29.24 29.24 29.24. Sure. Let's break down the bar chart and the provided data. Bar chart overview. The bar chart displays data from 2021 to 2030, with 4 different variables represented each year. 1. Manufacturing yield, blue bars. 2. Inflation rate, orange bars. 3. Economic growth, green bars. 4. Forecasted manufacturing yield, red bars. The left vertical axis shows the manufacturing yield, ranging from 0 to 30, while the right vertical axis shows the inflation rate and economic growth, ranging from -4 to 4. Data explanation. 1. Fourfold cross-validation scores, negative MSE. These scores indicate the performance of a predictive model using cross-validation. The values are -7.7284, -0.0676, -7.6176, -0.04. Negative mean squared error, MSE, values suggest the model's prediction errors. Lower values, closer to 0, indicate better performance. 2. Forecasted manufacturing yield for test set. The forecasted values for the test set are 24.88, 25.44. These values are represented by the red bars in the chart for the respective years. 3. Mean squared error for test set, fourfold. The MSE for the test set is 17.824. This value measures the average squared difference between the actual and predicted values. A lower MSE indicates better model accuracy. 4. Future forecasted manufacturing yield for 2027 to 2030. The forecasted values for these years are 29.24, for each year from 2027 to 2030. These values are shown as red bars in the chart for the years 2027 to 2030. Summary. The chart and data provide a comprehensive view of past performance and future forecasts for manufacturing yield, inflation rate, and economic growth. The forecasted manufacturing yield shows a steady increase, indicating positive future trends. Thank you.